Okay, so welcome everybody, Friday Arvo, we're on 7C.3 today, and what we've got here is a direct application of the average, the mean result of a probability distribution, so we'll get to recap that today. So just quickly, the mean of a probability distribution we also call the expected value, E of x, and that is the sum of each event multiplied by its probability. Okay, so here we're investigating a bit of gambling, really. We're investigating the nature of what constitutes a fair game. Okay, a game is fair. A game is going to be fair if the expected gain, the money you're going to get from winning it, is equal to the cost to play. Okay, that's the definition of what constitutes a fair game. If the amount you're going to earn on average from playing it equals how much it costs to play that game. So here, in our first example, we have a simple game costs $1 to play. All right, so the cost of play, I'll write that up here at the moment, is $1. It involves flipping a coin and guessing which side it lands on. If you guess correctly, you win $2. Okay, let the variable x be the value 1 during the game. So our possible events then are you can win $0 when you guess wrong, and probably a 0.5 probability of that happening, or you can win $2 if you guess correctly, which we expect to have a probability of 0.5 of occurring as well. So everyone happy with the distribution there? Excellent. So all we're going to do then is calculate E of x of this distribution and see if it's equal to the cost of play. So E of x is the sum of each result multiplied by its probability. And so we've got 2 times 0.5, we've got 1. And so in this circumstance, we have E of x, all right, the expected gain, how much you're going to gain on average, is equal to the cost to play. So on average, you pay $1 to play, and on average, you're going to get $1 back each time. So you're not gaining heaps of money, you're not losing heaps of money. This is a fair game. So we'll write, yes, it's fair, because E of x is equal to the cost to play. The expected gain is equal to the cost to play. Okay, there's 2 parts to this though. It says, would this be a good game for a fundraiser? All right, so if you're running a fundraiser, you're trying to make money, all right? So if I'm trying to make money, I don't want to play a game that's fair. I want to play a game where I win on average. So a fair game, any fair game, is not a good idea for a fundraiser. Fundraisers are always trying to rip you off somehow. So not good for a fundraiser because we won't make any money in the long run. Okay, so that's the basic technique that we're doing in this exercise. Let's get into a more complex problem. All right, we have a game that costs $5 to play using a standard shuffled deck of cards. So we'll say 52 cards, 4 of each suit, 4 suits, sorry, and then 13 cards in each suit. If you draw a face or an ace, okay, a face card, Jack, Queen, King, or an ace, you win $10. If you draw a 6 to 10 inclusive, you win $2. And if you draw 2 to 5 inclusive, you win $1. So you're always going to win money. Let's draw the probability distribution of it. So the events are, the lowest you can win is $1. You can win $2, or you can win $10. They're the possible events, right? So we've listed the events, and then we have what's the probability that the random variable, that the experiment, takes on that event. Okay, so you win $1, I'm looking at the last sentence, if you draw a 2 to 5 inclusive. So that means a 2, a 3, a 4, or a 5. That's 4 cards out of 13, okay? 13 because you've got 2 of diamonds, 3 of diamonds, 4 of diamonds, 5 of diamonds out of 13 diamonds cards, but there's 4 of each suit. So really there's 16 out of 52, which is the same as 4 out of 13. It doesn't matter which way you write it. Okay, a 6 to 10 inclusive. So that's a 6, 7, 8, 9, or 10. That's 5 out of 13. And then $10 if you get the wicked face or an ace. So the probability of Jack, Queen, King, or Ace, that's 4 out of 13. All right, so remember here, let's calculate E of X first. So E of X is equal to each event multiplied by its probability added together. So we have 1 times 4 on 13, plus 2 times 5 on 13, plus 10 times 4 on 13. All right, so that's 4 on 13, plus 10 on 13, plus 40. That takes us to 54 on 13. So it's going to be 4 point something. Get it exactly. $4.153. Okay, so remember we write 4 figures and then we round the third figure. We've got $4.15. That's the expected gain on average. Okay, is this game fair? The game costs $5 to play, so you're going to spend $5 playing, and on average, okay, the mean result is $4.15. On average, you're winning $4.15. Okay, the game is not fair because E of X is not equal to the cost to play. So we'll make that statement first. So something like that is absolutely fine. Not fair, not far. Not fair. Okay, would this game be good for a fundraiser? So let's suppose you're running it, okay? You're charging $5 on average and then giving back $4.15 on average every round. So on average, you're making 85 cents per time the game is played. So yes, this would be good as a fundraiser because it allows you to generate some profit. So we can even make that case. On average, you make 85 cents each time you run it. Okay, so we can all see $5 to play, $4.15 is what you're paying out. So on average, 85 cents each time. And this is how all casinos function. All casinos always have a slight advantage over the player. All right, so let's rip into 7C.3. That's probably just where we'll go today. We'll see how we're tracking along, maybe 7D.